Hello students, welcome to EPG Pathshala. I am Dr. P.K. Ahluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Statistical Foundation of Thermodynamics from paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We will learn how to understand the meaning of thermodynamic limit and importance of particle density, differentiate between macrostate and microstate of a system, understand the notion of equally likely possibility of each of the microstates of a given macrostate, that is, principle of equal a priori probability as the cornerstone of statistical mechanics. Count number of possible microstates for a given macrostate, leading to the idea of thermodynamic probability. Establish the meaning of statistical mechanical temperature, pressure, and chemical potential, and show its equivalence with the thermodynamical temperature, pressure, and chemical potential. Define statistically the Boltzmann formula for entropy, and ultimately to have a recipe for deriving thermodynamics from statistical root. This module has been developed for postgraduate level as per the following subtopics: thermodynamic limit, macroscopic state and microscopic state, principle of equal a priori probabilities, linking thermodynamics with statistics, thermal contact between two systems, notion of statistical mechanics temperature, mechanical contact between two systems, notion of statistical mechanics pressure, chemical contact between two systems, notion of statistical mechanics chemical potential, and recipe for deriving thermodynamics from statistical root. So, what is thermodynamic limit? The fact that macroscopic systems are made up of typically 6.023 into 10 to the power 23 particles points to the enormity of the systems involved. Thermodynamic limit is a way to express this enormity, and a natural way to express this by carrying out the limit number of particles n approaches infinity and volume V approaches infinity, such that the particle density n, which is equal to n upon V, remains fixed or constant. Taking this limit amounts to saying that extensive properties of the system vary proportional to the size of the system, that is, number of particles or volume V, whereas intensive properties remain independent of the size of the system. This process can be started with a finite system with a fixed density and keep on adding more and more such identical finite systems to it, such that number density remains the same, causing increase only in extensive parameters without change in intensive parameters. Not going to thermodynamic limit in the mathematical sense can lead to serious problems with the strict compliance of the extensive nature of extensive parameters such as entropy. There are two ways to characterize a macroscopic system in equilibrium under consideration. These two ways are macroscopic state of the system and microscopic state of the system. A given macroscopic state corresponds to a large number of different microstates, or what you call microscopic states. A macroscopic state, also called a macrostate, is described in terms of macroscopic variables such as total energy E, volume V, and number of particles n. In describing a macrostate, we are not at all bothered by the description of the properties of individual particles constituting the system, such as their momentum, spin, etc. A microscopic state, also called microstate, is specified by describing the state of each particle in a given macrostate. Counting the number of microstates in a given macrostate is the most basic task to indulge in statistical mechanics. How does the macro state of the system depends on number of particles of the system n, volume V of the system, and energy E of the system? This is the fundamental question which we are going to answer. To answer this question, let us take a system made up of n number of non-interacting particles with total energy E. This energy is the sum of the energies epsilon I of individual particles such that E is equal to summation over I Ni epsilon I, where Ni is the number of particles each with energy epsilon I. Obviously, total number of particles capital N is equal to sum over Ni. It may be recalled that epsilon I are the single particle energies which have two distinct properties. First, these are quantized, leading to quantization of total energy E. Their value depends on the volume to which they are confined. However, it is worth noting that as volume increases, the difference between the adjacent energy levels decreases rapidly and E goes from being a discrete variable to a continuous variable. Secondly, the microstates of a system under consideration is then defined by specification of N, V, and E. This macrostate can be realized at the microscopic level in many different possible ways known as microstates. In simple words, it implies that total energy E can be distributed among n particles constituting the system in large number of different ways. Quantum mechanically, this amounts to specifying all possible independent solutions of the n particle Schrödinger equation of the system under consideration with energy eigenvalue E. One of the aims of statistical mechanical formulation is to count the number of all the possible microstates. It is interesting to note that though a system corresponding to a given macrostate remains in a state of equilibrium, its microscopic states may keep on changing continuously. In this course, this number or count shall be denoted by Greek letter omega, which is a function of macroscopic variables of the system, which in the present case are n, v, and e. Therefore, this count is a number denoted by the function omega as a function of n, v, and e. The value 1 upon omega gives the probability of occurrence of any one of the states, which is as per the principle of equal a priori probability, the same for each microstate. This 1 upon omega is also known as thermodynamic probability, PR. The equilibrium state of the system then is the state for which function omega maximizes for each of its arguments. It is interesting to note that though a system corresponding to a given macrostate remains in a state of equilibrium, its microscopic state may keep on changing continuously. Principle of equal a priori probability. Allowing possibility of all microstates of a given macrostate via principle of equal a priori probability has resulted in derivation of ideal gas law and derivation of Maxwell-Boltzmann velocity distribution law, which were later confirmed experimentally. Justification of this principle therefore lies in the results derived from it and observed experimentally. This principle is treated as one of the postulates of statistical mechanics, linking thermodynamics with statistics. This link is established through the fact that the equilibrium state of the system is the state for which function omega of n, v, and e maximizes for each of its arguments, leading to three conditions of equilibrium for each of the microscopic variable E, V, and N. For this, we consider two physical systems, system 1 and system 2, which are separately in equilibrium, described by the macroscopic variables N1, V1, E1 and N2, V2, E2 respectively. System 1 has omega 1 number of microstates and system 2 has omega 2 number of microstates as shown in figure. Two systems are ready for making contact in three ways. A. When the partition is conducting. B. When the partition is made conducting as well as movable. And C. When the partition also allows for exchange of particles. Case 1. Thermal contact between two systems. Notion of temperature in statistical mechanics. Let us consider first the case in which N1V1 and N2V2 are kept constant, but energy can be exchanged by making the intervening partition conducting. However, in this case, the total energy E is equal to E1 plus E2 remains conserved. That is, E is equal to E1 plus E2 is equal to constant. At any instant, system 1 is equally likely to be in any one of the microstates omega 1, and system 2 is equally likely to be in any one of the microstates omega 2. Then the combined system is equally likely to be in any one of the microstates omega, such that omega nve is equal to omega 1 n1 v1 e1, omega 2 n2 v2 e2 is equal to omega 1 n1 v1 e1 multiplied by omega 2, which is a function of n2 v2 and e minus e1. Since n1 v1 and n2 v2 are constant, we can write 4 as omega e is equal to omega 1 e1 into omega 2 e minus e1. Omega, number of microstates of the combined system, here vary with e1 till equilibrium is established, and this happens until omega maximizes. The combined system then attains a macrostate which has the most number of microstates. The important point to note is that this macrostate of the system is that state in which the system spends the largest portion of its time and presents itself as an equilibrium state. Mathematically, this condition when applied to fifth means that the derivative of omega, which is a function of E and E1, with respect to E1 is equal to 0 when E1 is equal to average of E1, the equilibrium value of E1, and E2 is equal to average of E2, the equilibrium value of E2. We therefore obtained partial derivative of omega 1 with respect to E1 evaluated at E1 is equal to E1 average, omega 2 evaluated at E2 average, plus omega 1 evaluated at E1 average multiplied by partial derivative of omega 2 with respect to E2 evaluated at E2 is equal to E2 average multiplied by partial derivative of E2 with respect to E1 is equal to 0. Note, E2 is equal to E minus E1. Therefore, we can write above as follows. Partial derivative of omega 1 with respect to E1 evaluated at E is equal to average E1 multiplied by omega 2 evaluated at average E2 minus partial derivative of omega 2 with respect to E2 evaluated at E2 is equal to average E2 multiplied by omega 1 evaluated at average E1 is equal to 0. Or if we rearrange, this becomes 1 upon omega 1 evaluated at average value of E1 multiplied by partial derivative of omega 1 with respect to E1 evaluated at E is equal to average E1 is equal to 1 upon omega 2 evaluated at average value of E2 multiplied by partial derivative of omega 2 with respect to E2 evaluated at E2 is equal to E2 average. Or we can rearrange it and it becomes partial derivative of log of omega 2 with respect to E1 evaluated at E1 is equal to E1 bar is equal to partial derivative of log of omega 2 with respect to E2 evaluated at E2 is equal to average E2. Do note that log here is to the base E. This equation 7 is the condition for equilibrium of the system 1 and system 2, where we define beta is equal to partial derivative of log of omega with respect to E evaluated at E is equal to E average with constant V and constant N. So 7th equation implies beta 1 is equal to beta 2. If we recall that the temperature is defined by the derivative of the entropy with respect to energy E as delta S upon delta E at constant N and V is equal to 1 upon T. On comparing equation 8 and 10, we find that delta S upon delta log of omega is equal to 1 upon beta T is equal to a constant. Equation 11 was first established by Ludwig Boltzmann. He also underlined the connection between the two approaches, that is, thermodynamic approach, equation 10, and statistical approach, equation 8, and further concluded that the constant in equation 11 should be a universal constant, which was later named as Boltzmann constant by Planck as S is equal to Kb log of omega. Also, 1 upon beta T is equal to Kb, or beta is equal to 1 upon Kbt. According to formula 12, one can get entropy of a system by knowing the total number of microstates of a macrostate for a given system. If omega is equal to 1, this corresponds to a unique, completely ordered state with entropy S is equal to 0. As omega increases, the number of microstates increase, and more is the number of microstates, more is the entropy. Therefore, in a given system, disorder is manifested through the count of the microstates of a given macrostate of the system. Larger this number, larger is the disorder, and less the degree of predictability. Furthermore, maximization of the number of possible microstates or probability amounts to maximizing the entropy for equilibrium. Case 2. Mechanical contact between two systems. Notion of pressure in statistical mechanics. If we extend the considerations of the case 1 and further relax the constraint on the partition separating system 1 from system 2 by making it movable as well as conducting as shown in figure 1b, then the volumes of the two systems also become variables, though the total volume V is equal to V1 plus V2 remains constant. And besides the equation 7 corresponding to thermal equilibrium, which is partial derivative of log of omega 1 with respect to E1 evaluated at E1 is equal to E1 bar is equal to partial derivative of log of omega 2 E2 evaluated at E2 is equal to E2 bar. We have another equation which can be obtained in an analogous way as in case 1, giving another condition for the system to be in mechanical equilibrium as well. This means partial derivative of log of omega 1 with respect to V1 evaluated at constant N1, constant E1, and V1 is equal to V1 average is equal to partial derivative of log of omega 2 with respect to V2 evaluated at constant N2, constant E2, and V2 is equal to average of V2. And we can define another property eta, where eta is equal to partial derivative of log of omega with respect to volume evaluated at V is equal to V average at constant E and constant N. On comparing with, again recalling thermodynamic formula, partial derivative of S with respect to V at constant N and constant E is equal to P upon T. And we can define another parameter eta, which is delta S upon delta log of omega is equal to P upon eta T is equal to constant. Therefore, we conclude the equilibrium condition during thermal and mechanical contexts such that P upon eta T is equal to Kb or eta is equal to P upon Kbt becomes P1 upon T1 is equal to P2 upon T2. That is, T1 is equal to T2 and P1 is equal to P2. Case 3. Chemical contact between two systems. Notion of chemical potential in statistical mechanics. Next, if we consider, besides thermal contact, partition such that it not only allows thermal contact but also allows exchange of particles between system 1 and system 2 but keep the volume fixed, then only total number of particles n is equal to n1 plus n2 and total energy E is equal to E1 plus E2 remains fixed, but V1, V2, E1 and E2 of the two systems can change. So besides equation 7th, which is partial derivative of log of omega 1 with respect to E1 evaluated at constant N1, constant V1 and E1 is equal to average of E1 is equal to partial derivative of log of omega 2 with respect to E2 evaluated at constant N2, constant V2 and E2 is equal to average of E2. We have another equation which can be obtained in an analogous way as in case 1, giving another condition for the system to be in chemical equilibrium as well. Partial derivative of log of omega 1 with respect to n1 evaluated at n1 is equal to average of n1, constant E1, constant V1 is equal to partial derivative of log of omega 2 with respect to n2 evaluated at n2 is equal to average of n2, constant E2 and constant V2. And we can define another parameter mu such that mu is equal to partial derivative of log of omega with respect to n evaluated at n is equal to average n, constant E and constant V. On comparing with, again recalling thermodynamic formula, partial derivative of S with respect to n at constant n, constant E and constant V is equal to minus mu upon T. If we combine the three cases discussed above such that if we allow exchange of energy, change of volume and exchange of particles simultaneously, the conditions of equilibrium are T1 is equal to T2, P1 is equal to P2 and mu1 is equal to mu2. We get delta S upon delta log of omega is equal to minus mu upon T is equal to constant. Therefore, the equilibrium condition during chemical contact such that minus mu upon T is equal to Kb or mu is equal to minus Kb into T becomes mu1 upon T1 is equal to mu2 upon T2, that is T1 is equal to T2 and mu1 is equal to mu2. Now we have a recipe for deriving thermodynamics from statistical root. So we are now ready to derive thermodynamics from statistical considerations. Recipe is as given below. For the macro state N, V and E of a given system, count the number of all possible microstates accessible to the macro state denoted by omega n V E. The entropy of the system can be calculated by equation 12, which is S is equal to Boltzmann constant multiplied by log of omega, where omega is the number of all possible microstates. The intensity parameters T, P and mu can then be calculated by the following thermodynamic relations. 1 upon T is equal to partial derivative of S with respect to E at constant N and constant V. P upon T is equal to partial derivative of S with respect to V at constant N and constant E. Mu upon T is equal to negative of partial derivative of S with respect to N at constant V and constant E. Or alternatively, P is equal to partial derivative of S with respect to V at constant N and constant E divided by partial derivative of S with respect to E at constant N and V is equal to negative of partial derivative of E with respect to V at constant n and constant s, and mu is equal to partial derivative of h with respect to n at constant V and constant E divided by partial derivative of s with respect to E at constant n and constant V with a negative sign is equal to partial derivative of E with respect to n at constant V and constant s. As explained in module 6, with internal energy equivalent to E, rest of the thermodynamics follows from the following equations. Helmholtz free energy F is equal to E minus Ts. Gibbs free energy G is equal to E minus Ts plus Pv. Enthalpy H is equal to E plus Pv is equal to G plus Ts. Furthermore, specific heat at constant volume Cv and specific heat at constant pressure Cp are given by Cv is equal to partial derivative of E with respect to T at constant n and constant V. Specific heat at constant pressure is equal to partial derivative of H with respect to T at constant n and constant P. In nutshell, once one knows the entropy of the system, equilibrium behavior of the system can be known by using thermodynamics. So students, let us now summarize what we have learnt in this module. In this module, we have learnt about statistical formulation of thermodynamics of a system in equilibrium by knowing the accessible microstates of a macrostate of the given system. That, as per principle of equal a priori probability, each of the accessible microstates is equally likely to happen. We have learned that thermodynamic limit means n approaching infinity and v approaching infinity, keeping the number density n upon v constant. That entropy of a given macrostate of a system is related to the number of allowed microstates represented by omega as a function of n, e and v by the famous Boltzmann formula S is equal to Boltzmann constant Kb multiplied by log of omega. That equilibrium state of the system is that state for which omega as a function of n, e and v maximizes, which further means maximization of entropy S. That the equilibrium condition for two systems under different types of contacts are T1 is equal to T2 under thermal contact, P1 upon T1 is equal to P2 upon T2 under mechanical and thermal contact. In this case, if there is a thermal equilibrium, this amounts to saying P1 is equal to P2. Mu1 upon T1 is equal to mu2 upon T2 under chemical contact. If there is a thermal equilibrium, this amounts to saying mu1 is equal to mu2. That the knowledge of number of accessible microstates provides complete knowledge of the equilibrium thermodynamics of the system via Boltzmann formula. Thank you.